This class, we will essentially control an underactuated system. So one of the famous examples of an underactuated system is a double pendulum with a single actuator. So here are two links, and if only link one is actuated, that is, if there's a torque on link one, then it's called a pendubot. If there's only an actuator on link two, then it's called an acrobot. Okay, and the thing about the system is that the degrees of freedom here are two, that is theta 1 and theta 2, but the actuator is only one. So when the degrees of freedom m are greater than the actuators n, it is called an underactuated system. And as you can imagine, this is harder to control than systems where there are equal number of actuators. We've seen double pendulum, but there were two actuators, and you could just set a PED controller for each of those actuators, and you could get wherever you wanted to, but it's kind of hard for the systems. So what we'll do in this class is essentially balance control of an acrobot or a pendubot. Here we're trying to find a torque T, and that torque could be at this or the first or the second link, depending on which system you're looking at. And we're trying to identify these Ks, feedback gains, K1, K2, K3, K4, such that we are able to hold the pendulum upright in the upright position. We'll also introduce some disturbances to the system and see if it can still keep the pendulum in the upright position. What we'll do is we'll use a controller design method called Linear Quadratic Regulator, and we'll just focus on the acrobot, which is the system where there's an actuator on link 2 at P, but there's no actuator in link 1 or OO here. And once you do this and you figure this out, it's easy to extend this to the pendubot, or another famous underactuated system is the cart-pendulum system. There's a cart and there's a pendulum, and you can have an actuator between the cart and the ground, and you need to keep the pendulum in the upright position. So that can be extended from what I'm going to show you. So I have created another template called template_dbpendulum.zip. It's in the MuJoCo link, tiny.cc MuJoCo. Download that, rename it to, let's say, dbpendulum_Lqr, and make those three changes, which we've always been doing in the main.c make file and the executable Unix or run-win file. And then if everything looks good and works fine, then you should be able to see a double pendulum when you launch the run Unix file by navigating to the folder dbpendulum_Lqr within the shell. Okay, so I'm going to do that, and then we'll get started. Okay, so that's my file. Unzip it. Let's call that dbpendulum_Lqr. Okay, we'll make those three changes. Main.c. Here is main.c. So go to line 28. Let's change number 1. Go to make file. Uncomment the right flags for your system. So for me, it is the Mac, and then change the root to the folder name. Okay, we won't need this. I'll close it. Open the run Unix file for Mac and Ubuntu, or open the Win file for Windows, and change the folder name to dbpendulum_Lqr. Okay, all looks good. Let's navigate to this folder. My project, and cd dbpendulum_Lqr, and then run. Okay, so there's a pendulum which is upright. It's not falling because it's perfectly balanced. Okay. Okay, so with that, we are ready to dive into LQR. Let's have some theory before we get started. Okay, so what is LQR? If you have a system, a linear system, x dot equals ax plus bu, where a and b are represent the system dynamics, then we are trying to find a control input u, which is this, and where x is the state. such that x of t, the state, goes to 0. Okay, and here we're looking at infinite time, t goes to infinity. So what LQR does is it penalizes or minimizes a cost j, which goes as integral 0 to infinity x transpose qx plus u transpose ru. Here, q and r are design parameters chosen by the designer, and I'll show you how to choose them a little bit later. So once you set q and r, and then you know what a and b is, there is a calculation which tells you how to compute k, which is the feedback gain. In this case, the state x is going to consist of 4 numbers: the position of both links, velocity of both links, that's 4, and then the k will be 4 numbers, 4 constants, which when multiplied with x, 4 states, gives you one control u, which then is able to balance the pendulum. Now, what we'll do is, instead of looking at the equations, which gives you k, we'll use this command in MATLAB called Lqr, and the inputs are a, b, the system dynamics, qr, the design matrices, and it'll give you k. And once you have the k in MATLAB, we can then put it in C and then balance the pendulum. Okay, so Q and R, as I said, are matrices which you choose. One of the ways people choose these matrices is they assume Q equals identity. Okay, so I n by n, because n is the degrees of freedom for x, which is in this case 4 by 4. R is the matrix multiplied with U. You choose it to be rho, which is a constant, times the identity matrix M cross M, where M is the size of U. In this case, U is M is 1, so I is going to be the number 1. And what we do is typically we design, instead of designing these Q matrix, which is 4 by 4, 16 numbers, and this is R, which is 1 number, so 17 numbers, we just design one number, rho. Okay, so rho is, if you set rho much, much smaller than 1, okay, so imagine rho is 0.0001, then it'll give you large gains. That is because it'll allow you to become as large as possible, which means that the gains will be large. Vice versa, if you put rho is much, much greater than 1, then you'll see that the U tends to be smaller and smaller. So if you have a highly constrained, highly control limited system, then you want to do is you want to choose a very high rho, keeping in mind the limits on your actuators. Otherwise, you just want to choose rho much less than 1, which will give you good control over the system. Okay, so this is a designer choice as well as a choice based on your actuators. Another thing to consider is the sensor noise. If there's more sensor noise, then big gains will amplify noise. And so you don't want to have big gains. So you want to keep rho as small as, as big as possible so that your gains are small. Okay, so we'll use this trick to control this double pendulum. Now, the problem with applying LQR is that it works only for linear systems, a linear quadratic regulator. It's a linear regulator. How do we apply it for a nonlinear system, such that x dot equals fx comma u, where x is the state, again, u is the control? What we need to do is we need to linearize this equation and get x dot equals ax plus bu. And when we talk about linearization, we're linearizing about some set point. So if for a pendulum, which we're trying to balance upright, our set point is the vertical upright position. So x equals 0. So how do you do that? Well, let's say that x0 is some reference set point, x0, and the corresponding control is u0. So we can write x dot equals fx comma u. We do a Taylor series expansion for x. So we replace x0 with x0 plus dx. So left-hand side changes to x0 dot plus dx dot. Here we can write this as, and I've skipped that step, this should be written as f of x0 plus dx, u0 plus du. And then you need to do a Taylor series expansion. It is the first term. This is this term plus the linearization. So df dx times dx, df du, plus higher order terms involving dx square and du square, which we will ignore. So they're cancelled. We know x dot equals f of x0 u0. That's true. So we can cancel that from the equation. And we are left with delta x dot equals, in this case, I replace df dx as a. and df du is b. And so delta x plus b delta u, right? And so once we have a and b, we can then proceed with the linear quadratic regulator. So we've done work here to figure out what the a and b would look like. The issue here, though, is how do you compute a and b? For this system, you need to compute using df, dx, df, du. What's f? F is basically the dynamics of the system. So x dot equals f. So this is basically, if you have a system, you need to use Newton-Euler's equation or Euler-Lagrange equations, which we've not done, but it's one method to find the equations of motion. The simplest one is a ball falling under gravity. You have x double dot equals minus g. So that's the equation comes from Euler-Lagrange, so, or Newton-Euler. And so that is what we want. Okay, now MuJoCo computes this inside, and we have access to the numerical value of f, but we don't have an access to the analytical value of f. So when we want to find df dx, we cannot do that analytically because f is not available in closed form. So we need to use what we know as finite difference to find df dx and df du. You know, doing the linearization, let's figure out what f is. Okay, so what is f? So equations for double pendulum look like this. Mass matrix, which is actually a function of q, only the angles, times q double dot, which is the acceleration, plus n q dot. Here you would have gravity term and Coriolis terms equals the external torque. So here m is, in our case, specific example, m is 2 cross 2. N is gravity Coriolis, dimension is 2 cross 1, it's a vector. T is an external torque, its dimension is 2 cross 1. For a pendubot, T would be U0 because the first link is actuated. So U is the only thing you can control, and you cannot control that torque on the second actuator. For acrobot, that U will be reversed. It will be on the second row because it's the second link, which is what you can control. Okay, so now we have x dot equals fx comma u. We need to find what f is. What we'll do is we'll invert this equation. Okay, now, as I said, analytical formula is not available, but numerically we can do this. That is, we take this equation here and we solve for q double dot. If you solve for q double dot, you have m inverse times t minus n. And what q double dot has within it is the acceleration, which is q1 double dot, acceleration of the first link, q2 double dot, acceleration of the second link. And that is what you get. Now, in MuJoCo, you have access to m. You can set torque to whatever you want, and n is available to you. So we can find q1 double dot and q2 double dot as a number, not as a formula. So in order to find f, all we need to do is concatenate all the rate of change of the state. So in this case, the state is position and velocity. So we need to find the rate of change of position and rate of change of velocity. So rate of change of position of the first link is q1 dot. The rate of change of velocity of the second link is, first link is q1 double dot, which by the way is here, which we found from this equation. Okay. Q2 dot is the rate of change of position of the second link, which is the velocity, it's available to us. And Q2 double dot is the rate of change of velocity of the second link, which is the acceleration, which is available through this equation. So we can get numeric values for this, which we put here for Q1 double dot, Q2 double dot, but we also have numeric values for velocity of both links because this is a state which we keep track of. So this is what is F1, F2, F3, F4. And that F, I can write it as with the inputs. There are 5 inputs to it. I give in Q1, Q1 dot, Q2, Q2 dot, and U, and out will come the outputs. So as long as I've developed the code to compute outputs, I'm all set to do the next step, which will be the finite difference. But before that, let's try to write code to compute f, this function f, whose inputs are these 5 numbers and outputs are these 4 numbers, rate of change of these 4 numbers. So let's do that in code and get f, and then we'll proceed to the next step. So I'm going to do that in code now. Yes, the first part is to write this function f, okay? And let's write it down right above, I think, my controller or init controller. Okay, so f I will have passed these variables to it, the model and D, without which we'll not have access to the state. Let me have the inputs. And as I said, the inputs are 5, and then the outputs are 4. Okay. I need to send in the inputs, and then the outputs is I'm sending it back to this function. So what I need to do now is find a way to, so let's define all the inputs and outputs, and then we use that to do more work. So our state is q1 dot, or let's call it u1, q2, or u2. Okay. So our inputs are the state and the controls. I shouldn't use u1. We got it q1 dot, q2 dot. The outputs would be q1 dot, q1 double dot, q2 dot, q2 double dot. Okay, so let's see how we can get these things. So q pos 0 equals input 0. So now what I'm literally doing is I'm supplying to this function the input 1 and setting it to the position. Okay, and you'll see why I do that later on when we try to find the finite difference. Then I would set the second one. Okay, and then I need to keep doing that for 1, 2, and be 1, 1, and there'll be 2 and 3. And then the final input is CTRL equals input 4. Now, before I do this, let me quickly check my actuators to see if I set the actuator correctly. So if you open the pendulum.xml file, okay, this is my double pendulum XML file. You can see that I've set the actuator, and this actuator is on pin 2, and pin 2 is my second link. So I've actually set it up to be the acrobot. So that's good. Okay, so this takes care of the input. What I need to be able to do is I need to be able to set the output 0, and that should be q1 dot. Yeah, I need to still define them, but let me just set it up so I know what needs to be done. 2 equals q q2. Okay, so that's now let me take care of specifying these. Let's first specify the first outputs because they're quite easy. q2 dot. We know that q1 dot is nothing but the velocity. q2 dot is nothing but the velocity of the second link. Okay. Now q1 double dot and q2 double dot as the one which I require to invoke the equations of motion in order to figure out what they are. Okay, so let's do that. So this is sort of something we've done in the past when we talked about control of a single link pendulum. We basically got the equations of motion from that. I'm going to use the same things, same code from there. So remember that the equations of motion is the way MuJoCo saves this is mass times QACC plus F equals CTRL. Okay, this is actually Q FRC files, and yeah, that's it. So remember, what I'm trying to do here is achieve here is I'm going to try to find QACC, which is equal to inverse of M times CTRL minus QFRC. So I need to get QACC, and QACC is the one which is equal to Q dot Q2 double dot, because it will be a there'll be two elements to it. Okay, so first I will obtain my M, QFRC bias, and CTRL, and then I'll use those to evaluate this function, which will give me Q1 double dot and Q2 double dot. So let's just do that. Okay, so this is code from previous time. We just write NV times NV is 0. NV is a variable which defines the state. So in this case, we have we have 2 degrees of freedom. So it's constant NV equals 2. You can also get this file if you print the model. If you go to simulate and say print model, you will see NV in one of the lines, and that's 2 for the system. Okay, so that gives me, that is initializing the mass matrix. To compute the mass matrix from the MuJoCo function, the function is called full M. Its syntax is you send in the model, you sending capital M, the mass where you wanted to populate the mass, and then you give this particular pointer ID. Okay, so that basically what it does is basically populates the mass matrix at that particular instant of time. Okay, so that let's now let us get the, well, we have FRC bias. Okay, we need to compute this. So we need to get the inverse of mass matrix. So let's get the inverse of the mass matrix. So remember, this mass matrix would be, will have 4 terms. M would be M0, M1. Okay, that will be the first row. And then there'll be M2, M3. So it's saved as a 1-dimensional matrix. Okay, so now let's get the inverse. So this is a formula which, it's kind of easy for a 2-dimensional system, but for a more than 2-dimensional, it's hard to do this to get an analytical formula. So the formula I'm going to use here is as follows. I need to find the determinant of M, and that is M0 times M3 minus M1 times M2. And then I need to get the, I think it's called the cofactor of M. Define this inverse. So the way this is defined, the inverse is defined is the cofactor divided by the determinant of the matrix. So cofactor comes out to be, or is the adjoint, I forget what it is called. So M3 minus M1 minus M2 M0. Okay, but to get the inverse, we need to divide by the determinant. So I less than 3, I less than 4, plus M inverse I equals M inverse I divided by determinant of M. I think I've not defined I is int I. I think this looks good. Okay, so we've got this. Now all I need to do is compute this term and then multiply with inverse M, and that would give me QACC. So what I'm going to do is I'm going to define this QACC double, or let me call it, I guess it's okay, QACC. Its size is NV equals 0. Okay, let's store this entire stuff in some variable called, let's call it F. F NV equals 0, and I'm using F to save these lines. So it would be so CTRL is, so remember that my first first link doesn't have any control. So that should have a 0 plus minus p pointer q frc plus. This is the CTRL, which is 0. And then f2 equals, now I would have the control because this is underactuated and the second link is actuated. So d q frc plus. I think that takes care of f. F equals this. Okay, now I'm all set to find QACC. Okay, I'm going to invoke one of the functions used in one of the past classes, which is in MuJoCo, which is used to compute the product of a matrix times a vector. The inputs to this is first you give the desirable output. So ACC is my output. What I need to supply now is the matrix itself, which is M inverse. And then I need to tell it what F is, what it multiplies with, so F. And then this, since this is 2 by 2M, that's all I need. And so now it multiplies M inverse with F, and I get the result in QACC. Okay, so QACC is, let's add this. So I've done this computation. Okay, now we've got this. The whole purpose of doing this was to find Q1 double dot, Q2 double dot. So we can now get those. Q1 dot equals QACC 0 and Q2 double dot equals QACC 1. So I think I've connected the dots here. I've got everything I needed. Okay, now that we've figured this out, we can now test this function. So let's take this function and call it from init controller. So now I really want to test it once. So instead of having the simulation go for 5 seconds, I'm just going to run it for 0.1 second because I don't want it to run too long. It's only going to take, yeah.
It's going to fail. I think in your void F, you called it double inputs and outputs, but when you actually assign them, you put input without the S and output without the S. So you can just just get rid of the S.
Right, good catch.
On both input and output.
Yes, thanks. Okay, let's call this from init controller. Okay, the inputs are M, and then there's D. And I need to specify my inputs and outputs. Now I can give any value to this. So let's first define input to be 5, 0, output 4, 0. Just to get something interesting, let me specify one of the inputs. The first one, which is position as 0.1. Okay, and clearly I want to see what the output looks like. So output 0. Okay, so once I run this, I should see something interesting because think of it this way. If I perturb the second link and the control is 0, then I should see that the system gets disturbed and moved, right? Actually, it might be best for me to increase this time to see what happens in the animation too. okay, there is a problem. This is not a number. Okay, so there's some calculation problem in my Q1 double dot Q2 double dot. Let's go back. Okay, there's something wrong here. That's why these are coming infinity, because it's first and third. Okay, so we need to debug this. Let me see if this looks good. Printf. Oh, F1. This should be F0 and F1. I don't know if that was the problem. Maybe that was a problem. I don't know. It's still none. Okay, that was not it. Let me just print it. Okay, those was 0. Okay, but that's probably not the reason. It's probably the M inverse which is causing the problem. Let's see. So let me know if you see the bug. Okay, this is the bug. That M is not. M is basically 0, 0, 0. That's why it's coming. So why is M 0? I thought this would give me this would give me the full state. Okay, so the problem is that once you set this state, you need to pass them to the model and update the data vector D. And if you remember properly, sometime back I showed you that unless you call MJ step or MJ forward, this will not happen. So what I'm missing here is calling MJ forward. So once I set the state, immediately let me call MJ forward. Hopefully that will fix it. Okay, it's got fixed. This is the mass matrix. And now the state is non-zero. So it's saying the velocity is 0, but the acceleration is not 0. This is what I expected. Okay, so that's that. Let me comment this. And then let's try this one more input. Let me try to put a different control. So input, so that was state number 5, which is 4. If you start from 0, 0.1. It looks okay to me. Yeah, that's what I would expect. You can also try to put velocity and see if that works for a velocity perturbation. So 1.1. So you should see 0.1 here if it's all right. 0.1. Interesting. It doesn't affect the other things. Okay, so I think we've got successfully the function f, which is basically the bulk of the work. Now, what I'm going to show you next is probably much easier than what we've done so far. Okay, so talking about linearization now, A equals df dx, B equals df du. What is f? Well, f is, as I showed you, it was this 4 output variables, q1, q1 double dot, and so on. X is the input, the state, q1, q1 dot, q2, q2 dot. So if I want to find the A matrix, it's df dx. So it will be 4 cross 4. So I need to do this df1 dq1, df2 dq1, and so on. So it will be a 4x4 matrix, and B would be df du. It will be a 4x1 matrix because U has dimensions of 1. Okay, so how do we compute this? Well, this is how we'll do it. We've created a function f already. First, let's compute a nominal f0. to get a nominal F0, all I need to do is send in the nominal control and nominal state. So in this case, we're trying to balance up over the upright position. So that state would be 0, 0, 0, 0. So let's compute F0 first. And then we'll go to the next step. So everything will be done here. First, all the inputs are set to 0, 0, 0. So all I need to do now is get F0. So let me define double F0 4 equals 0. And after this is run, I need to set them to the output. So F set into for equals 0, I less than 4 plus F0 I equals output. Okay, I've not defined I, so let me define that here. Okay, and then we can check. Well, we can check, but there's nothing really interesting here. It's basically 0, 0, 0. It's all 0, 0, 0, which is expected. Okay. Okay, so we've got F0. Now let's compute. Let's perturb the first element. So first element is Q1. We'll add some perturbation. Now this is really a choice you can make. You can have a very small value, but if you give too small a value, let's say 1e negative 7, it will not work well because our integration tolerances are kind of small. If you make a big value, then calculus tells you that it won't work because that finite difference only works for small values for x. So we have sort of there's actually a trade-off. So you need to find a value small enough, but not too small. So let's just define, I'm just going to use a perturbation of, look at the integration is 0.001. I would say 10 raised to 4, negative 4, 5 will be fine, but let's just use a perturbation of 1e negative 3. So let's define that 1.001. Okay, so the first step, we perturb the first input. First input. So input 0 equals, the initial state is 0. So I just need to put a perturbation. And I need to call this. And now let me define another variable to store my f. So double f1 equals 0. So call this, and then I don't want to. And of course, save this in a similar fashion. Let's run this. Okay, so that's when you perturb it, this is the state you get. Let's see what needs to be done next. So once we perturb the first element, we compute a new f. We called it f1. And in order to find the first column of A, we need to take f1, which is this f0, which we already computed, and divide everything by perturbation. So in this case, since it's a first column, and the first column has 4 elements, 4 rows, I need to do it, either do it 4 times, or I can just write a for loop, which basically keeps track of A. So let's define A to be a 4x4 matrix, and then populate the first column of A using this formula. So let's first, let maybe here define double 4 equals 0. And then, as I said, we now need to populate. So for 0, I less than 4, I plus plus. So A. So this is, remember, it's the first column. So it's going to be AI 0 equals. Now I could use F1, but let me take a shortcut. Let me not. I Okay, this is extra lines of code, so you don't have to do it. You can have to do F1. You can just specify output I minus F0 I. It basically does the same thing without defining an extra variable. Okay, so this is exactly what I've been asked to do here. So to compute the first column, I do output from the perturbation minus F0 divided by the perturbation. Okay, so I don't need F1, so I'm going to delete it. And then I don't need this, take this. So next, so I need to compute the second column. For that, I perturb the second element and then do the same thing. Now, one thing you want to remember is this input is already set to PRT. So we want to reset that to 0 before we set the second element, which is number 1, equal to pert. So I just suggest setting up everything to 0 before you proceed. So I equals 0. That just takes care of, I can just copy paste this code. Otherwise, I have to individually define each of them equal to 0 before I start. So this should be 0 to 5, I think. There are 5 inputs. So input is I equals 0. That's just setting all of the inputs to 0. Next, we set the input 1 equals pert. Then we call F. Then we compute the second column. So 1. And that will give us the second column. Now, we can do a little bit of automation here. We notice this pattern, that is this 1, right? And that's the thing which you need to change. So I can copy paste this, but then I have to change this 1 to 2 and so on. So let me just define a new variable j. Okay, and then this j is set to 1. And then this j and j. So once I set j equals 2, I can do this for the second and so on. So it looks like I can take this, paste it, LBJ2, and everything will be taken care of. And then, oh, if I mean, another way to do this is actually write a for loop. I'm just breaking it down into multiple steps. You could write a for loop on J, and that's probably much better than what I'm doing here. Okay, I'm going to run this just to be sure that it runs fine. Okay, there was nothing I wanted to print. Since it works, I'm going to just use the same thing over here, so just to make it uniform. So Bj equals 0. Okay, so I think at this point we've populated A. So let's print A, printf for I equals 0, I less than 4, I plus plus, for j equals 0, j less than 4, j plus plus, printf A, I, j. And then for it to look exactly like MATLAB format, I need to put a new line here. And so let's see what this does. Okay, so that's what A looks like. I guess this is okay. Now let's compute B. To compute B, what we need to do is instead of perturbing Q's, we need to perturb U. So just do the same thing, perturb U this time, and then do minus F divided by. So let's first define B. B is going to be just a single dimensional array. So B4 equals 0. And I can actually reuse this code. So in this case, the input is 4, which is the 5th element. All this is set to 0, which is good. And then the 5th element is set to pert, right? And then this should be giving me B. So B, there's no J here. Yes, so I can now print %f E I. Okay, let's see what we get. Okay, that's B. Okay, now what I need to do is, as I said, I would eventually take this A and B, take it to MATLAB, and produce the what do you call it? The LQR command to get me the gain matrix. So what I need to do is, well, I need to copy, paste, and then change this, and I might have to do it multiple times. So what I do is I try to print it in such a way that I get a solution which is compatible with MATLAB. So I just do copy, paste, and it gives me what I want. So here's what I would suggest doing. I want A. I'm going to write it in the way which MATLAB likes it. So MATLAB wants it A, open bracket, dot, line. Then once you print each line, it wants a semicolon. And then it wants it to end it in this fashion. And then let's make 2 of these. So if you run this now, okay, so it produced A exactly the way I can copy paste it in MATLAB. So it makes my life easy. We can do the same thing with B. Right here. B. And we can just put this here and in the bracket. Okay, so A, B. So it's all ready to go to MATLAB. Okay, so the next step is to compute the gain matrix K, right? So what we do is we use K equals LQR ABQR. So I'm going to use the same design technique I talked about earlier, where we define rho to put a weight on R, and that's how we'll design the controller. So let's go to MATLAB. Okay, I need to be in this folder. Oh, there's already something in MATLAB. Let me just run this. Oh, I didn't change the folder. Let me just put this in here and run this. It'll ask me change folder. And now I'll be in this folder without me having to do anything. Okay, so if you do pwd, we're in this folder. Okay, so I don't need this file. Get a new one. Just save it as main LQR. So we'll see clear all. Clear all. Okay. So all I do is now take the A and B. I think it's going to give an error. Oh, it just worked fine. Okay. We got A and B. Now we need to define Q and R. So let's define Q to be I, which is identity matrix. R is row times identity matrix 1 by 1, which is just 1. And I need to specify row. So let me start with row equals 1. Okay. So we've got QR, and we just need to find K. K equals LQR A B QR. Can run this. Okay, so out comes the gains. I need to take these gains, put it in my simulation, and run the controller. So let's me copy these. Go back, head back to my code. Now I need it to be called every single instant of time. So the place I put this is in my controller. Double K4 equals that. That's one thing. The next thing is I need to actually specify the controller. So ctd ctrl 0 equals minus k0 times t q pose 0 minus k1 into d q well 0. So k0 1 2 3 1 1. There is one issue though, which is when I call init controller and I call, so let's say I call init controller, it basically calls f. F calls mj forward, and mj forward basically calls the callback, which is my controller. So every time it calls my controller, it will execute this, and I don't want it to execute this part of the code because it has init CTRL0. So it's going to redefine the CTRL0, and that's not what I want. So what I'm going to do is I'm going to set this so that it comes on whenever I want to. So I'm going to by default set a flag, some variable called Lqr, which will be off. And the moment I finish doing my call to init controller, I'll turn that flag on so that this my controller code is only executed when the controller is ready to go. So what I mean by that is this. So let me go and up and define a flag, and we turn the flag off. Then my init controller code is called, which is right in main. It's called here. And I want the flag to be on only after this is called, so that A and B are set. So Lqr equals 1. So now it's on. Once it's on, I want to go back to my controller and tell it that to run this code only if Lqr equal to 1. So it will bypass calling this until init controller is done calling. So with this, I think I'm all set to try this out. So let me increase the simulation time to 10 seconds. Okay, nothing is happening here because I have not quite perturbed the system, so it's doing nothing. So let's perturb the system. So let's go right to init controller, where it's defined. Here I can set the pose. So you could set the first, and you'll see that it doesn't work for too big a perturbation because it's based on linearization. But let's just put a small perturbation of 0.01 to the first state. It's doing a good job of balancing, as you saw. You can try increasing this. I don't need to go 10 seconds. Let me just go to maybe 5 seconds is going off. Yeah, it's good. Let me ramp this up to 0.05. I don't think it'll work. Yeah, it just goes crazy. I could do this for link 1. I could put negative. I could put it to velocity. Zero. But that should be a little higher, I think. Let's try higher perturbation. It goes crazy. Okay. I have another option. If you think that it is likelihood that higher gains would give me a better control, I can go back to my MATLAB code, and since I want higher gains, I would change the row to, I guess, 0.1. So you can see it's 265 for the first one. Let me run this, and you have minus 468. It became twice. I can do 0.01, and now it's like 1000. So let me try this 1001 and see if that makes any difference. So go back to my controller. Remember, all this is 1 times 1000. Let's see if this makes any difference. No, it's trying, but doesn't really work. So it works for a kind of narrow range. Let's try 0.1. Nope. See if I have luck with 1. So since 1 is the second link, it might actually work better for this one. No, no. Something makes me feel that it's not going to work for anything. Let me just try changing this to back to 0. And I know that this one worked. Position.
Professor?
Yeah, it's not working.
Chenming suggests that I think he's saying that you're missing the 1000 multiplication of 1000 by the gains.
Oh, not for, I didn't do it for all.
On
Right?
one of the, yeah.
That's why it wasn't working. Right. Good catch. Let's, so this should work. Let's check that once. Okay, it works. And then we'll go to the original one, velocity. That was stripe 0.1. There's so only so much it can do. This seems to be too high for it. Yeah, that it works. And I think it'll work if I perturb the second system. So let's try that. Works. I think this is it's much more better on the second one. The first one, let's try 0.1. It works. Yeah. So this one, yeah, that's what I expected. It will work better on the second. If the perturbation is the second link, this will fail probably. Oh, it just works too. Okay, so here's so this is how you can check it. Now there's another way to check, and this will be the last part I'm doing. Okay, so we already saw how to check the controller by perturbing. So we just perturb Q pause and Q val, and then we balanced it. But that's just single disturbance and shows the effect. What you can do is something more interesting. You can apply noise in my controller. So we could generate noise using one of the functions in MuJoCo called MJU standard normal. So this generates noise, I think, of standard deviation 1 and mean 0. And then we can apply disturbance in 2 ways. One is FRC applied. This basically applies a Cartesian force in the X, Y, Z direction. So we'll choose to apply it in the X direction, which is the horizontal direction. Or we can apply a force in the joints. So joint 1 and joint 2 by using QFRC applied. So let's try that. So let's go to my controller. Right here. we only want the noise to play in once the control is set on. So Lqr equal to 1. Following MJU standard normal. Okay, and then it needs the noise intensity. Sorry, it needs a variable to be passed in. So let's call that noise, and then pass that variable as a pointer. And as I said, there are two ways to apply this. One is we can use XFRC applied. Okay, and so this is basically 6 times body plus I. So the way this works is if you want to apply it on body number 0, then there are 6 ways to apply it. There is a force in the XYZ, there's 3 numbers, and then there is torques in the XYZ direction. So since we're talking about body 1, because body 0 is the ground, we have to take body 1, so 6 body plus, we want it to be a horizontal linear force, so it would be element 0. So forces in the XYZ would be 0, 1, 2, and then torques would be 3, 4, 5. So that should be nice. And of course, if you want to increase the intensity, you put 5 times or 4 times or whatever you want. So now with this, let's test the controller. So you can see it's shaking because of the noise, not too much. We can increase the time so we can watch it a little longer. Let's go to X. First applied. Okay, so let's do it, I don't know, 5 times noise. Okay, that worked. We can try 10 times noise, probably fail. You could apply this to body 2, that was the first link. This is applied to the second link now. And it failed. Maybe this is too much. Okay, looks like that's working. Okay, one more thing and then we're done. So you can also apply noise this way. QFRC. So this is either 0 or 1. 0 stands for the first joint, 1 stands for the second joint. So if you want to apply the first joint, you just do this. Okay, that's the first joint. You can apply it to both joints if you want. Okay, and then you can apply all of them together. You'll probably fail. Okay, looks like it works. Let's try similar for body 1. That works too. So, you can play with these noises. You could also do is you can go to double pendulum. You can add sensor noise through this. And then in that case, what you want to do is If you add sensor noise, I would add the sensor. So I would define sensors for the first link, sensor for the second link. So there'll be 4 sensors. What you then do is you'll go here and you'll change this from DQ pose to essentially sensor data, and you can introduce noise that way too. And then you can see how what the response.